Alright guys, welcome back to another episode, or in fact the last episode of Polly's Introduction to Computer Network this semester. There's just one special to-do to announce, that is no lecture next Tuesday. So this is effectively the last lecture of the semester. Okay, so do use the time next Tuesday to prepare for the exam on Wednesday. And so we do have quite a few topics remaining today. We just finished talking about the routing algorithms. That's chapter 5.2. We do have 5.3 and 5.4 to talk about today before we can have these questions in the exam, okay, in 5.3 and 5.4. So let's go ahead and start. First, let me introduce chapter 5.3. Okay, and the term called autonomous system, the AS.
Next, we'll be talking about two routing protocols that are actually running on the internet. First is called the Ospf, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, Vgp, is then based on the other routing principle, the distance vector routing. Well, to be exact, Vgp is not just distance vector routing, it's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, okay, Ospf is the routing protocol that runs predominantly within a network, a local network. While BGP, this other one, very, very critical, very, very important, is running on all these backbone routers, okay, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple, and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. So until now, the way we're introducing these routing algorithms is actually very idealized. Okay? Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. Even taking a distance vector routing algorithm, which is already more scalable than link state, if we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, there's going to be how many? Yeah, these many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, okay, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes, okay, for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like, close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not going to work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch, okay, you don't want to go there. Okay, so even if we use a more scalable routing algorithm, distance vector, okay, consider it working on the internet, not going to scale. Okay? We cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also going to swap the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 gigabyte of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay? So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers, okay, nearby belonging to another organization, another system. Now each of these systems can work independently. The network admin hired by the organizations could decide independently, autonomously, okay, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, okay, the system admin can decide maybe distance vector routing is better, okay, more scalable, better. So all routers here then will be running the distance vector routing. Okay. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, okay, one or two routers and make them the delegate routers. These delegate routers, okay, at the higher level will interconnect. Okay, so this system's delegate routers and this system's delegate routers, they might interconnect. Okay? And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all these routers in the backbone is going to run one routing algorithm. Okay, so distance vector or link state. Okay. Well, to just tell you ahead of time, okay, for internet, backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. Okay. So you see two levels of hierarchy. Yeah, there's backbone network, and then each delegate router there associated with it is a local area network. Okay, so internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems.
All right, so that is what I meant. Those are smaller networks that are under the same administration is called a autonomous system, an AS. So within an AS, you run an inter-AS routing. Another AS runs another inter-AS routings. And then these ASs, okay, among them will run another routing. But each AS is one destination. So you can see that some sort of distance vector running between the ASs or inter the ASs will scale to the number of systems there are instead of number of IP addresses, which is still a lot. Okay, if it's IPv6 as you heard in the video. Even distance vector, if we have a vector with all potential IPv6 addresses, okay, for each entry, it's still not going to scale. So that's why we break the internet apart. ASs, inside ASs, you're sending data based on the destination addresses. But there's another level higher that you're passing data from AS to another AS. Okay, when it arrives at the destination AS, the destination AS's routing will send the data to the destination IP address of the individual host. Okay, so that's the general idea. The next video is going to introduce more how the intra-AS routing within a system and the higher level inter-AS routing will interact. Okay, so obviously there are two routings. They somehow need to work together, right?
Once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Now, routers belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Now, each AS will also pick powerful routers, usually sitting at the border of the AS. These powerful routers, I call them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. So gateway is what? The doorway. Yeah, the routers sitting at the border of these AS connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border, of its own AS, and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol, okay, running in the backbone of the internet is called the inter-AS routing. Okay, so that is the routing protocol that's running across the gateway routers. So this is the routing, working among the ASs, and the gateway router there will be doing the inter-AS routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have 3 ASs, 1 here, 2 here, and 3 here. You see individual routers interconnected within one AS. Okay, so there are 3 here for AS2 and 3 more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, but you see 1B and 1C, both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So these 2 gateway routers. Just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. And inter-AS routing is running in between. 1B, 2A, 1C, 3A, and so on and so forth. Now, the focus of this slide is to talk about how would the forwarding table look like when we have 2 levels of routing running on the internet. Now, let me show you an example here. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-AS routing algorithm. It would also be contributed from the inter-AS routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, not within the region, right, you need intra-AS routing to find the gateway router. And you also need the gateway router to find, hey, where's the destination gateway router? Right, so you do need inter-AS routing algorithm telling each node where to pass data further. Just like you need intra-AS routing there telling you how to reach another router within the AS. So forwarding table here will be configured by both intra and inter-AS routing algorithm. The intra-AS routing determines the entries for destinations within the AS. Within AS. And inter-AS determines entry for the external destinations. To be precise, the inter-AS determines which gateway, which router here you should be passing the data to. But intra-AS will also be telling 1D here to go to that particular gateway router, what is the right way. So you see here, interplay of inter-AS and intra-AS routing for packets going outside of the AS.
All right, so essentially for internal destinations, you rely on the intra-AS routing. For external destinations, meaning destination outside of your AS, how do you establish a forwarding entry? Well, you need inter-AS routing telling you which gateway router in your AS to forward the data to. Right? Because that gateway router would then forward the data to the next AS that's along the way to the destination AS. And the intra-AS routing is still necessary because intra-AS routing will tell you the exact path to go from you to that particular gateway router, that would know the way to go to the destination AS. So that's the interplay between intra and inter-AS routing. The next video is going to tell you a little bit more with more detail.
To make sure the interplay of the intra-AS and inter-AS routing is more clear, let's take a step back. Look at AS1 here, 1A, 1B, 1C, and 1D. So these routers within AS would run the intra-AS routing. Therefore, they would know the shortest path going to each other. No problem. Now, at a higher level, at the inter-AS routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AS1. 3A, obviously a gateway router for AS3. But you see here, 3B having also connectivity to outside to another AS. 3B is also a gateway router for AS3. Similarly, 2A, 2B, 2C all have links to outside to other ASs. So they are also gateway So these gateway routers at the higher level will be running the inter-AS routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AS1 to AS2, the shortest path is to go directly from AS1 to AS2. Now, if there is another AS here, AS4, for example, okay, then the shortest path might be to go from AS1, AS2, and then AS4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AS to the destination AS? What is the next AS to the destination network? Okay. So we might have another AS here, AS5. Then the shortest path from AS1 will be what? AS1, AS3, and then AS5. Okay. With those said, we may now walk through the scenario here. Let's suppose a router in AS1, say 1D, and it's got packets to go outside of the AS. Let's say AS5 here. Okay. Now, we see the shortest AS path will be the what? A1, AS3, and then AS5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router. So this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AS routing. They do not participate in inter-AS routing, but they need still to know the shortest AS path to these destination ASs out in the world. Okay. So 1D, 1A don't do inter-AS routing, but they still need to know the inter-AS path. So they must learn the inter-AS path, which is to know for each destination AS, is it AS2 or AS3 being the next hop AS to the destination AS? And this is essentially the inter-AS routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AS routing. So 1C and 1B thereafter, inter-AS routing will then propagate these AS path information to all routers inside AS1. Okay. And so propagation of the AS path, just like computation of the inter-AS path, would also be part of the job of the inter-AS routing.
Okay, so you see, even though the internal routers runs only intra-AS routing, but these internal routers also have the inter-AS path information stored. So that's how they figure out which bordered gateway to send for destination that's outside of AS. All right, now we have a healthy general picture of intra-AS routing, inter-AS routing, a hierarchical routing architecture of the internet. Now, let's zoom in into each level. First is the intra-AS routing, the lower one. Okay, the one inter-AS routing that's running in the backbone, we'll talk about that next. So the first video about intra-AS routing is just to introduce generally what intra-AS routings are and the existing protocols.
The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within an AS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay. And then running on these internal routers within an AS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay. But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution. okay, in the 1980s, late 80s. And it's based on this principle, distance vector routing. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. But this other one, OSPF, short for Open, Shortest Path First Routing Protocol. This one, on the other hand, is very popular. Okay. So Open here stands for open source. Okay. RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, OSPF is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, okay, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, okay, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, OSPF for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the Idrip, Igrp, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, okay, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking. Okay. So if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, okay, in SDN, pretty much are doing what? Generalized forwarding, okay, and allowing the flow table being installed, and that's pretty much all, okay. There's no need of running routing algorithms on individual routers. So starting from 2016, Cisco stopped maintaining Idrip because there's really no need, very little need of doing routings inside the router.
All right, so with Idrip being obsolete, RIP being resting in peace, the only one that's still popular being used is OSPF.
Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the OSPF. Open here stands for, yeah, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, okay, they'll be sending these reports in OSPF message. These OSPF messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all. Okay. There's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cause of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of OSPF, designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of OSPF. First of all, okay, these OSPF messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. One can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, which is nice, okay, sometimes. for each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay. For example, if we are trying to serve less effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, OSPF allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so Multicast Ospf, MOSPF, is a very nice and easy extension of Ospf. Oh, by the way, one can also configure Ospf to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3. Okay. Inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay. Some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay? So at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay? The link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. So that's how the area border routers discover each other at the higher level. Okay? And those advertisements will be shared by also the backbone routers and the boundary router.
All right, so that was intra-AS routing. And now we move one level higher, the inter-AS routing. Well, what's different in inter-AS routing from intra-AS routing is that in intra-AS routing, we do have multiple protocols or designs available. At some point, they are popular, okay, one over another. But in inter-AS routing, there's only one protocol, okay, that is called Vgp. And here's the big overview of Vgp.
Now the second big category, the inter-AS routing. There's in fact just one protocol defining the category, the Vgp. Now this is also the routing protocol that runs on all these gateway routers. Okay? that are higher in the internet routing hierarchy. Ospf, Idrip, those are the intra-AS routing. So those runs on the regular routers, okay, within an AS. Now, network admin gets to choose one intra-AS routing protocol versus another, okay, as long as all the routers within the AS runs the same routing protocol. Similarly, at the higher level, these gateway routers, okay, in order to find a way to reach each other, they need to run the same routing protocol as well. You see, there's no need of having an alternative, okay, inter-AS routing protocol. Therefore, BGP here is the only inter-AS routing. Very critical. It plays the role of enabling all these packets being exchanged, okay, in the core of the internet. We'll talk more about BGP, but let me share just a little bit ahead of time. BGP here is based on the distance vector routing. To be exact, okay, it's based on the path vector routing. So in distance vector routing, the router tracks for each destination what is the shortest distance and what is the next hop, okay, along the shortest path to the destination. In path vector, okay, so this one running at the inter-AS level, the source AS will track for each destination AS what is the entire AS level path. Inter-AS level paths. So that inter-AS level paths will contain all the intermediate ASs, okay, along the way from the source AS to the destination AS. So what's nice about keeping track of the entire AS path is this. The source AS knows by default what is the next hop AS. And by counting the number of ASs along the way, you get a rough sense of the path cost as well. But the downside of tracking the entire path is that the memory requirement is higher. But this is okay, right, at the inter-AS level because we try to aggregate destination IP addresses, right, into prefixes. Okay? And if we do that as much as we can, we are not actually storing a big vector containing one entry per IP addresses. Okay? Potentially, we just have a low number of these prefixes, okay, to span the entire IP address space. So path vector is exactly what BGP, this one and only inter-AS routing, is based on. First line, BGP stands for Border Gateway Protocol. And once again, it is the one and only inter-AS routing protocol that's holding the internet backbone together. To be more precise, it allows each AS the following. First, it allows the gateway router there for the AS to receive subnet reachability information from the neighboring ASs. This is very similar to distance vector. A router receives distance vector, okay, from the neighboring routers. So the gateway routers in the AS receive path vector from the neighboring AS's gateway routers. So by subnet reachability information, we meant the path for each destination subnet for each destination AS. Okay? And there are many of these destination ASs, therefore, we receive the path vector, okay, from the gateway routers of the neighboring ASs. Second step, the gateway router receiving such a path vector will then propagate it to all the internal routers, okay, including those routers are gateway routers to other neighboring ASs. Okay. As a result, okay, each of these routers within the AS can calculate what is the best path for a particular destination AS. The calculation can be based on what's provided in the path vector. For example, the path length, right? Or based on the policy of the organization owning the AS. Now, this is more and more likely the case how a router determines what is the best route. Okay? The policy can well be profit-driven, business-driven, security-driven, and things like that. And in the end, when a good AS path is selected for a destination AS, the border router there, then can append, the AS's AS number to the AS path derived, and then further propagate this to the neighboring ASs. Okay, so that completes the cycle of receiving path vector, doing the calculation, and then pass the path vector on to the rest of the internet. Right? And of course, at the beginning, the AS gateway router will announce itself, right? So each AS is potentially a destination. It will announce itself's existence to the rest of the internet.
All right, so that's the overview of VGP. You see that it's based on distance vector, but not exactly distance vector. It's called the path vector. Instead of sending distance only, it's sending the exact path. Another thing that's a little bit different is that, remember earlier in the general overview, there's interplay between inter and intra-AS routing. Okay, so BGP being the inter-AS routing. Individual routers sitting down below, okay, will still need to know all these paths. So BGP, okay, not only propagate the path vectors, receiving path vectors, update to find a better route, it also propagate these AS passes to the internal routers within an AS. Okay, so that's something that BGP does in extra. Next, let me illustrate BGP, how BGP sends these reachability information, aka the AS path.
One last point to make is just this: the reachability information, aka the path vector. When they travel across the border, go from one AS to another AS, this is actually part of the exterior BGP protocol. So in exterior BGP protocol, we establish the exterior BGP connections to allow path vectors travel across borders from one AS to another. Now for path vector, that is supposed to be sent internally to all the internal routers, then belongs to the IBGP protocol, and they are sent through the interior BGP connections. And these are actually illustrated using this picture here. Okay, so if we focus on AS2, we do have two gateway routers, 2A and 2C. So you see these gateway routers connecting to other ASs, and there are exterior BGP connections to outside, exterior BGP connections to outside. So eBGP, in red color. But in addition to that, 2N and 2C both need to send path vectors internally. Okay, so you see they went through the IBGP connections. All right, so IBGP connections in blue. So once again, these are gateway routers, and the gateway routers you see having both the red connections and the blue connections. They run both the eBGP part of the protocol as well as the IBGP part of the big BGP protocol. Those BGP connections are often referred to as the BGP sessions. So these routers will exchange messages over semi-permanent connections. The reason that they're called session is probably because it's semi-permanent, so it's on all the time, and occasionally you take it down and then restart it. Okay, so semi-permanent TCP connections. Now, TCP. BGP is a routing protocol, right? These messages we send should be at the layer 3, but TCP is actually a layer 4 protocol. Okay, how do you like this? On the other hand, TCP allows reliable data transfer. So would you prefer the path vector? So these messages that we're exchanging between the BGP routers, the path vector is being sent reliably or not? To push it a bit further, what about using TLS, the secure version of TCP? And if we use TLS, these BGP messages, these path vectors, will look more like an application level message. You think about it, you debate within yourself. Now, the messages we're exchanging between the BGP routers over the BGP sessions are these. The paths to all sorts of destination networks, the paths to all sorts of destination ASs. In fact, altogether, we just call it the path vector. So BGP, again, a path vector protocol. And let me give you an example here. So let's say in AS3, there is a prefix X. And this is the destination for packets coming from maybe AS1 or AS2. So AS3 that learns about this destination will need to announce, advertise it to outside of AS3. So 3A here, will need to announce its existence and pending its own AS number, so AS3 here. So this will be the AS pass, being advertised. This will be the AS pass being sent in the BGP message to the other end of the exterior BGP connection, to the other end of the BGP session. So 2C here, will receive the AS pass, AS3, X. So AS3's gateway router 3A will advertise the pass to AS2's gateway router 2C. So when AS3 does this, it's also saying that AS3 promises AS2 to relay packet, okay, on behalf of AS2 so that it can reach destination X. Right?
All right, so that was a very simple example illustrated. Now let's look at a couple more examples that are a little bit more complex in a way that the BGP routers do have choices. Okay, there are multiple paths available to the same destination. How does one pick a path? So that's involving the policies. So one could decide which path is better as AS paths are being imported. One can also advertise or explore paths based on the policy as well.
Let's go over a couple more examples so it's more clear where the import policy and the export policies are applied. So this is the same example we saw earlier. Destination network is here, X, okay? And so AS3 there is gonna send the path advertisement, okay? That looks like this, AS3, comma, X. Okay? And this is gonna reach 2C of AS2. So AS2's router 2C receives path advertisements like this. And this is through the exterior VGP connection. And the advertisement came from AS3 and from router 3A. So 3A of AS3. Now, if you recall in the very early slide, right? The border router here will then propagate the AS path throughout all routers in the network. But no, there's import policy. So the exact process is more like this. 2C there will actually check AS2's import policy. If the policy says 2C, it's okay to accept the path, then 2C propagates the path to all routers internal of AS2. Okay. So sending of these AS paths internally is through the interior VGP connections. Right? So the import policy actually happens before the propagation of the path, okay, to all the routers internally. And then, 2A here, receiving such a path, can then prepend itself and pass it further to the neighboring ASs. But wait, the export policy is applied here before passing on of the advertisements. Let's check. If 2A here is allowed to advertise the discovered path to AS1 here, okay, then we form the new advertisement AS2, AS3, and X, and then send it to 1C that belongs to AS1. Okay, so once again, before the prepended, the extended AS path can be advertised further to the rest of the internet, we check the export policy. Right? Second example is a bit more realistic. So 3A here, the gateway router of AS3 might have multiple eBGP connections to outside. Okay, so in that case, a gateway router might learn multiple paths to a destination in AS3. So let's see. One of the paths is this, right? AS3's 3A sends AS3X, okay, as an advertisement to 2C. 2C checks the import policy and therefore pass it on to all the routers internally. 2A picks it up, checks the export policy, and let's say that it's just allowing advertisements of the path further. So prepend AS2 to the path and then send it further. At this point, 1C learns the path AS2, AS3 to destination X. And the way to go is for 1C to send to 2A. The other direction is this. 3A can be simply sending what? AS3X, okay, this path advertisements directly to 1C. And 1C will just simply learn, right? There's another way to reach destination X, which is just simply sending it to AS3 through 3A. Okay, so these are the gateway border routers that 1C send the packets to, okay, for the two different paths, 2A and 3A. At this point, 1C sees two advertisements coming in. Before 1C propagates any of the paths further, okay, it needs to check the import policy. Okay, so AS1's gateway router 1C there, and we need to choose. It could choose one of the two, or it could just take both of them. Okay, let's say that 1C chooses AS3, comma X, yeah, sure, the shortest AS path, and advertise it to all routers internally of AS1. Okay. This is the second example.
All right. And last is the reachability information. How do they look like? The advertisements, they are called sometimes.
Let's say more about the messages we exchanged in these Vgp sessions. So these messages are essentially path vectors. Inside the path vector, we have lots of these path entries, okay, or route entries. Each path in the path vector of Vgp is this: the destination address. Now, because in BGP we are sending packets to a destination network, therefore, to address to a destination network, we use the prefix of the destination network. And then attributes. Now, in path vector, the most important information there is the path. Therefore, you see, okay, in the set of attribute here, we need to definitely have the AS path. So AS path is the most important component in the set of attributes. There we see the list of ASs. Okay, it takes from the source to reach the destination. The discovery of the list of ASs, the discovery of the AS path, however, okay, came the other way, from the destination network. Okay, so the destination network is going to advertise its prefix, okay, and so that's going to be in an advertisement message. Okay, so the whole AS of the network X, okay, let's say AS2, receiving such an advertisement at the gateway router, okay, that gateway router is going to prepend itself, okay, prepend the AS number, okay, AS number 3, okay, before X, and send this out as the prefix advertisement to the neighboring AS. The neighboring AS, let's say AS2 there, receiving such, okay, an advertisement is going to prepend itself before it sends out further to AS2's neighboring AS. So now AS2's neighboring AS receiving such an advertisement will then discover, right, a path to go from AS2, AS3 to destination X. Okay, so list of ASs through, okay, these paths, the prefix advertisements as traversed. Okay. So that is the AS path. One and the most important, okay, part in the attribute set. Second important is this, the next hop. Now, this is not quite, okay, the next hop AS, the next AS number, okay, in the AS path. No. It is actually the gateway router, okay, within the source AS that is directly connected to the next hop AS. So it's carrying the IP address, okay, of the gateway router, leading to the next hop AS. So the two together necessary forming the attribute set. Now, BGP routing, okay, has grown more and more being policy-based, okay, meaning the gateway router, they're receiving these prefix advertisements. Okay, it's not like for every advertisement they will actually prepend its own AS and then pass it down further to other neighboring ASs. There'll be some sort of import policy. Okay, so the gateway there receiving the advertisements will have to say, okay, will have to decide. Some of the advertisements they will decline, and some others they accept. Only the ones they accept will be propagated further to all the routers within the AS. Okay. Now the gateway routers, okay, in the AS receiving these accepted, okay, advertisements will then decide whether to prepend themselves and then pass the expanded advertisements, okay, to the other neighboring ASs. Okay. But you see, there are also policy, okay, the AS might apply before these other gateway routers, okay, advertise the expanded, okay, AS path to the neighboring ASs. Okay, so some of them actually might have complex policy that is very fine-grained. For example, if one gateway router, okay, connects to two other neighboring ASs, this gateway router might say, I send this particular extended advertisements only to one of the ASs. Yeah. Policy to import and policy also to export.
Yeah, I know. You guys are probably wondering what these policies can be. What I can say is that we'll be spending quite a bit of time in the second hour to talk about policy. And you guys will be asked through a series of quizzes to set policies in case you are the admin of a particular AS. Okay? So in the second hour, before policy, we just have some more detail about BGP to talk about, and then the rest of time will be about policy, and that'll be all. Okay, so expect 4 quizzes coming in the second hour, and that take us to the break time. Okay, so let's take a break, 10 minutes, and we'll come back at 11:20. So there's an interesting question from Catfish. So I thought that I talked about it a little bit. So AS numbers of each AS, it's not like, randomly formed. In order for an organization to try to be a part of the internet, they need to apply to be a part of an AS or form an AS itself. So NTU, I just do whois of the PA workstation's server IP address, and this is what I found. NTU belonging to AS 17716. Okay. But if you look into the detail, you'll see that the domain is in fact moe.gov.tw. So this is the Ministry of Education. So Ministry of Education has applied for being an AS, and all the universities, I guess, university networks in Taiwan all belong to AS 17716. Okay. And to get this number, you register to this organization, APNIC, Asia Pacific Network something something. Okay, well, maybe I should look it up to find exactly what it is. Some sort of Asia Pacific community something. Internet Registry administrating IP addresses for the Pacific, okay, Asia Pacific. All right, so I mean that's the idea. So the stuff we were talking about on the slides, they are for real. Okay, yeah. And you know what? It's time to come back to the lecture. So the next is this. We know the inter-AS routing is BGP. And we know the chances high that the intra-AS routing, for example, what Poly is doing now, sending data, is more likely OSPF. How does OSPF interact with BGP? Okay, this is what this video is going to talk about.
Let me borrow example 2 here and continue to talk about this. How a router sets up a forwarding table entry, okay, for a destination outside of the AS. Okay. Yeah, scenario the same, destination being X. 3A, the gateway router of AS3 has 2 eBGP connection, therefore 1C here potentially can receive 2 AS paths. And 1C, according to example 2, chooses the shorter AS path. So let me run the animation. So 1C discovers 2 paths and picks the shorter path. And this shorter path is further propagated internally to all routers. So 1A, 1B, and 1D will learn about the shortest path to destination X from 1C. And what 1A, 1B, and 1D will do is, well, if I receive ever any packets with destination X, then I will forward the packet towards 1C, the border router, okay, they receive, okay, the AS path from. To make it easier to explain what's coming up next, let me just label, okay, for 1A, if the packet is supposed to go out on this interface, then we call that interface 1. And yeah, for packets to go out on this other interface, let's call it 2. Okay, similarly for 1D, this is interface 1, this is interface 2. Now, 1D here, okay, has discovered there is a path to destination X that is going through 1C. Okay, that is what 1D knows so far. To add an entry into the forwarding table for X, 1D needs to know exactly which interface, is it 1 or 2, that leads to 1C. How would 1D know that? Yeah, call the intra-AS routing there. Okay, let's say it's OSPF. Okay, so OSPF is going to tell us if the destination is 1C, what is the link, okay, along the shortest path to 1C. Okay, so that happens to be 1, so we will fill this entry here, okay, interface column being 1. Similarly, let's try to derive again for 1A. Okay, so 1A knows, for destination X, I should be forwarding packet towards router 1C. So let's call intra-AS routing and find out from OSPF, what is the shortest path to 1C, and which link, is it 1 or 2 on the shortest path? And we'll get 2 here, and 2 here would forward packets to 1D, and 1D here we see earlier will be forwarding packets over this direction and reaching 1C. Therefore, going backwards and reaching destination X.
All right, so that was a very simple case. In the next case you see, you will also feel that maybe doing policy-based routing at the inter-AS level makes a lot of sense. Doing shortest path routing at the inter-AS level probably isn't all that worthwhile. Okay, so next video, check out the hot potato routing here.
Route selection. Now, this mechanism is necessary for slightly more complicated scenarios. Let's go back to example 2 again. Right? We have this router 1C being the gateway router of AS1. So you see towards the end of the scenario, AS1 discovers 2 AS paths, one from AS3 to go to destination X, the other from AS2, and then via AS3 to go to destination X. So in the previous slide, we say the policy of AS1 is such that we only select this to import. And so 1C propagates this AS path to all internal routers. Internal routers will then send packets, destination being X, through 1C and therefore being forwarded to AS3. Very simple. But what if we relax the import policy a little bit further so that 1C here cannot discard this other AS path? As a result, 1C will need to propagate both paths internally. So each of these routers internally will see more than one route to the destination X. Ouch. Yeah, so that's when we apply the route selection. So internal router there will need to apply route selection here to decide which of these two it will send packets to. The process is like this. Step number 1, check the local preference of these routes. So if you recall earlier, a route is what? Composed of the destination network's prefix and a set of these attributes. So we know that AS path is one attribute. Next hop is one attribute. There's one more attribute called the local preference. So this one actually weighs the highest. So BGP actually checks the local preference first and take the path with the highest local preference. So local preference there is usually to indicate, between the two neighboring ASs, AS3 versus AS2, does AS1 prefer forwarding packets to AS3 or AS2? So if AS3 is preferred, AS3's path, so this guy here is going to carry a higher local preference. Now, if there's no local preference specified, then we go to step 2. So the internal router, let's say 1D here, will then check which of these multiple paths to destination X give us the shortest AS path. So in the scenario, 1D is going to pick this one. Now, if both AS paths have the same path lengths, then we go to step 3. We pick the closest next hop router. 1D here sees 2 paths. The next hop router for this path is going to be 1C. The next hop router for this path here is going to be 1C as well, because 1C is the border router receiving these advertisements. But if you consider a slightly different scenario, so again, we have AS3, AS2, and AS1. So the router now in the limma is now 2D. 2D here actually sees 2 AS paths. One AS path is actually coming from 2C. 2C is the gateway router connecting to AS3, which it receives a path to X, AS3, X. 2A is the gateway router connecting to AS1, where AS1 is passing another AS path to AS2. That is AS1, AS3, and X. So 2A passes this path to 2D. 2C also pass on this path to 2D. So 2D in the end learns, there's one AS path through next hop 2A, this guy. There's another AS path through 2C, this one. 2D here, assuming that abandon the shortest AS path phase, goes straight to the closest next hop router phase. then we'll do this. For this pass, next hop router is 2A. For this pass, next hop router is 2C. 2D here will consult. Okay? The intra-AS routing again to find out, is 2A closer or 2C being closer? So if you see the scenario, 2A distance to 2D is only the link cost between 2A to D, which is 201. Distance between 2D to C, however, is 263. So 2D here is going to choose 2A to forward the packets to. So it's going to choose AS1, AS3, and X, this other AS pass, which is actually longer, okay, than this other one to pass the data. This is also very well known as the hot potato routing. Allow me to explain. Yeah, so 2D is this guy holding a hot potato. So yeah, the packets are almost like these hot potatoes, and 2D can't wait to get rid of these packets. So 2D wants to be able to pass the hot potatoes, the packets, as soon as possible. Therefore, picking this poor guy here, 2A, to throw all the hot potatoes over. Okay, distance is shorter.
Yeah, so you see that the internet routing is doing all these strange tricks, hot potato routing. So even though there are multiple AS paths at the internal router actually throws the data as soon as possible to the whichever gateway router that is the closest. Okay. And there's a good reason for doing hot potato routing. That is because the ASs, some can be huge, some can be small. So just to send data within an AS can take a long time already. And so you have two AS paths. One path is a little bit shorter than another, but you don't know the exact distance, okay, to travel from within each of these ASs along the path. Okay. So a shorter AS path, the physical length of travel might be longer. Okay. And that is why BGP is turning more and more like a policy-based routing instead of being more like distance vector, trying to find the shortest path. Okay, so that is yet another major difference of BGP to distance vector routing principle. Now there's just one very short message talking about BGP's message format. There are 4 kinds of messages in BGP protocol.
This is the last slide of the BGP protocol. Okay, so in BGP, the protocol, it actually defines 4 types of messages. Okay, so not just the message we mentioned earlier containing the pass vector being passed in the BGP sessions. Okay. There are other types of messages that BGP sends. So some of them are actually to send the pass advertisements, to send the pass vectors, but some of them are to establish the TCP connections, okay, for the session, or to tear down the TCP connection, or to keep the TCP sessions alive. Okay, let's go through these BGP messages. The first type is called the open message. Yeah, the first purpose of it is to establish the TCP connection. Okay, so the sending peer there will be sending an open message to the receiving peer. Okay. Receiving peer will be sending back an ACK for that message. As a result, the 2 peers establish a BGP session. So the ACK of the open message there is going to be in the keep alive message format. Okay, I know it's a bit tricky. Now, the open message is also used to do the authentication. Okay, so the 2 peers can authenticate each other to make sure that the pass advertisements, okay, are indeed the true pass, okay, to be discovered. Now, update message. So this is the message being used to send the past advertisements, the past vectors. So this message is also allowing the routers to withdraw outdated past vectors. Keep alive message we saw earlier, it's to ACK the open message to establish a TCP connection. Keep alive message is also being sent, okay, periodically to refresh the TCP connection, just in case there's no update messages being generated. So update messages is the past advertisements. Last is the notification message. Okay, so this reports in case there's any error in the previous message. Okay, and it's also used to close the connections for peers.
And finally, let's talk about the policies. Okay, So this video, very important, it's going to set the background for the series of quizzes coming up. It's 6.5 minutes. Pay attention.
One very important issue about BGP to discuss here is, BGP routing is very policy-based these days. If you recall, there's import policy, there's export policy, there's also local preference for route selection. There are lots of things the network admins can tweak, to decide where packet goes. The reason for those policy-based setting is this. Let me use an example to explain. Consider this network. We have 3 ISPs in the middle, A, B, C. They are the provider networks. W, X, Y are the customer networks. More specifically, W is the customer of ISP A. So W pays A some amount of money every month, and A will in turn help W passing packets, going out to the rest of the internet or coming in from the internet. Similarly, if the traffic is supposed to go out the other direction, right? So W pays A, and therefore A is responsible to serve W. Similarly, for this customer-provider pair, Y being a customer, C being a provider, X being a customer, B being a provider. Now, X is a little bit more complicated. It's multi-homed, customer network. So X here pays B and C. As a result, B and C should both be forwarding packets for X. In scenario 1, let's assume that there's a user in customer network Y here wanting to send something to the user in W. And so in order for W to draw in traffic from the internet, its provider A here will need to announce its existence. So AW here, an AS pass needs to be sent to the neighboring ASs, which happen to be ISP B and ISP C. So A advertises pass AW to B and to C. As a result, B is going to see this pass and prepend itself and see if this AS pass needs to be further advertised to yet another neighboring AS, such as provider C. Now, B's network admin actually knows better and choose not to do that. And the reason for that is because of this. If BAW is advertised to C, C is going to discover, this is actually one way for this user in Y to send traffic to user in W. And therefore, the traffic is going to go this way to W. And you know what? B here, B does have a customer X. X is paying B. But is W paying B? Is A paying B? Is C paying B? Well, based on the setup of the problem, WAC not paying B, and yet B is using the network resource here to transit the traffic for B and C. So B gets no revenue to do this route, BCAW, because CAW, based on the scenario setup, not paying B. So chooses not to advertise BAW to C is so that C does not discover this pass, and therefore, not using this pass to send traffic. Instead, C here receiving AW is going to prepend itself CAW, and Y is going to use CAW as a way to send traffic to the user in W. So you see, in this scenario, very obvious. For a customer network, ISP will be happy to route traffic to and from the customer. But the ISP not getting paid by others would hate to transit traffic between these other ISPs. So bottom line, not getting paid for the work. Scenario 2 is very similar to scenario 1. The network is completely the same, and we just continue scenario 1 from here. When B has discovered BAW is a pass to go from B to W. Now back in scenario 1, a min of B chooses to not forward BAW to C, so that we don't draw traffic this way. Nice. But B will actually have to send BAW to X, so X can discover XBAW is a pass. So just in case there's any user in X wanting to send data to user in W. Nice. So, makes sense. But, hey, X is dual home, so there's yet another connection to a neighboring ASC. So should the network admin of X here send XBAW to C? Well, let's assume that we send XBAW to C. In this case, C is going to discover CXBAW is a path to send data to W. Similarly, Y is going to discover YCXBAW is a path to send traffic. YCXBAW is a path to send traffic from a user in Y to a user in W. And that's going to travel like this. How do you like this? Well, from X's network admin's point of view, hey, this traffic is actually not for me at all, right? It's actually between Y and W. Y pays C, W pays A, and no one is paying me, and yet I'm paying B and C. Okay, so it's a big no-no for X here to send XBAW to C. All right, so X will not want traffic coming from C and simply transiting to B. So X should not be advertising anything to C, okay, coming from B. So again, money is the issue, all right? So X is not getting any money from C or from B. Therefore, X is not happy transiting traffic for these other ISPs or even from other customer networks not paying.
All right. So bottom line, $sign. Okay, because ISP is a business. We pay to get access to the internet. ISP, these provider networks, get paid so that they can establish the infrastructure to allow us to get on the internet. Okay, essentially, no free lunch. Okay, is the general policy that these ISPs are considering. So let's walk through these four quizzes and see if you can pick up some skills setting up policies for each of these provider networks. Quiz 47 is the simplest. Okay, the network looks identical to the network in the video. Okay. So the bigger clouds are the ISPs, the provider networks. Smaller circles, X, Y, and W, are the end customers, okay, customer networks. And in this series, there will be data constantly coming from node Y, from network Y to a user in network X. Okay, so data should be traveling from Y to X, and quite often. All right. And this is a network very similar to the example in the video, but if you pay attention in the previous video, there was a link in between BC in the previous video, but in this network it's simpler. It's a tree network. All right. So let's go over the setup. X is the customer of B, okay, and X pays B. B, being the provider, then is responsible for forwarding traffic coming from X to the rest of the internet. B is also responsible for forwarding traffic to X. Traffic's coming from the rest of the internet and destination being X. All right, so X pays B for the money. X pays B some money. And the goal is not just to forward data for X, but also to forward data coming from X, but also to forward data destination being X. Okay, so B is responsible for forwarding traffic in and out of X, both directions. Okay, so that money is paying for traffic in both directions. So Q1 asks, should B advertise the AS path BX to A? And tell the reason. Q2, do you think A should advertise the AS path ABX to C? And the reason. So this is now thinking generally. Should A advertise the A is passed? So X will announce its existence to B, and B learns that to go to prefix X, there is a pass, BX. B then will be thinking, should I advertise BX to A? Okay, in order to allow Y to send traffic to X. Should B do this? Q2 very similar. If B does advertise BX to A will then learn the pass to prefix X, A, B, X. Should A advertise this pass to C? Okay. All right, so this is the easiest of the quiz series today. So let's go to the Slack channel W15 quiz 47. Yeah, Polly has already posted the quiz 47 side there. We do have 3 to 5 minutes for you to work on this. All right, do tell your reason. And let's begin counting time. All right, yeah, as I said that this is probably very easy to judge. So team 5 is saying yes because that's the only way, right, to get to X. Similarly for Q2, A should also advertise AWX because that's the only way to go to X. Yeah, but there's a yeah, I think team 2 is seeing the same thing, right? Although that the scenario was that Y is the one sending data often to X, but W might want to send data to X as well. Oh. Yeah, so if it's not connected, what can you do? Right, and some other people in Y might want to send data to X. Okay, and that's why team 4, I love team 4's solution here. So yes, so later on W and Y can send data to X. So Team 4 here sees that, okay? Y and X are not the only users on the network. W can potentially want to send data to X as well, not just Y. And here, Team 4 is debating whether A should send AWX. Yeah, because obviously A is not get paid by X or Y. A is obviously not paid either by X or Y, right? So A is definitely, right? Thinking twice, 3 times. It is a slightly harder decision for A. So, very good. Very, very good. Okay, you're thinking. Jason, well done. Okay. But maybe yes. But maybe yes. Because C there might not want to have any business with A if A is cutting C off entirely, isn't it? Yeah. So you can probably tell that on the internet, the connectivity, the reachability is almost like a social network. It can be a little bit political. You kind of need to be nice to others in order for others to be nice to you as well. But you're not getting any revenue. Okay, so there are probably things you can do, but there are probably things you cannot do but to cooperate. Oh, yeah, so hey, Polly doesn't like politics. Well, Polly doesn't understand politics. Do you? Human beings are the most complicated machines there are. All right, let's see Keke from Team 10. Yes, it should, right? X pays B. B should make sure that X gets connected to the rest of the internet. And B is only connected to A. B has no choice. B must send that advertisement, BX, to A. Q2, Keke was saying, yeah, it should, right? Otherwise, it's the network is just disconnected. But maybe not. I think maybe it's more that A want to negotiate with C. So that A gets some money from C. And C can raise the price of Y subscribing to C, isn't it? So obviously, A want to send the AS pass ABX to C, but in the meantime, negotiate with C. All right, good. So Keke also debating. Okay. Yeah, and Team 7 is obviously thinking, hey, it's a tree network, right? If A does not send ABX, then provider C and the customers of C will all be disconnected. That's a major deal. That's a major issue, in fact. All right. Yeah, I see that some teams are just saying, for sure, A must send that ABX pass out because that's the only way to connect to the rest of the internet. And some were saying that I need to, but I'm not quite sure. Yeah, maybe I can get some payment, right, from Y through C. All right, very good. I think you guys get it. Yeah, Guan Yu saying, no, it's selfish. No, being selfish, no, yeah. If the scenario is just strictly as Polly said, yes, of course. Okay. All right, very good. You see, policy is I see you guys' solution, right? Some will say strictly no. I'm not getting money. I'm not letting you through. Okay. You know what? That's usually what you can do also to force C to negotiate with you. I don't like that. I don't know how to do that. Okay, it's a mind game. All right, so I hope that you guys like the setting policy for Vgp, because the next quiz is coming up, number 46, which is more complicated. Sorry, 48. This network then is more like the network we saw earlier. Okay, so this is the case that the X is not dual homed. Okay, so you see that there's a connection between B and C. So what's a little bit different in quiz 48 is that I also draw the money flow. You see that X pays B, Y pays C, W pays A. Customers pay the providers. But the providers, right, they also need to forward data back and forth between each other. Yeah, these providers can be paying each other as well. So in this scenario, you see that B is paying A, B is also paying C. And this usually happens when B and C are providers that have been here for a while, okay, well established, okay, older ISPs. And B is more likely a newcomer trying to join in the competition for the consumer market. Okay, in this case, very often B pays the predecessors money for a resource. Okay, so Q1 of quiz 40A is asking, let's suppose A and C charge B equal amount of money to forward data for B. Okay, and suppose you are now hired by B. Should B advertise BX to A only, to C only, to both of them, or to at least one of them? Again, you probably see also several possibilities, right? So what do you think the best way to do it? Okay, in case A and C charges B equal amount of money. Q2 is asking, so as I'm drawing the arrows, right, pointing from B to A, B to C, one is thicker than the other. That means in case C charges B more per unit data, A charges B less per unit data. And again, you are hired by B, so you need to be thinking in the perspective of B, trying to make profit for this newcomer ISP B. Should B advertise BX to A only, to C only, to both of them, or to at least one of them? Okay, for both Q1 and Q2, provide your reason. All right, so this is slightly easier. Let's give it 5 to 7 minutes. And let's start counting time. Yeah, let's take a look at the solutions we have so far. So team 7 is that saying, hey, send to both. Okay, it's not fair to send the advertisement to either one of them. Yeah. I think, sure. And if it's equal charge, yeah, of course. And you get multiple ways of forwarding data or taking data from other sources to X as well. Yeah, but when you say fair, you might want to talk about what do you mean by fair? What's the fairness here? Okay. Second, should advertise to both. Same as Q1. Although we can advertise to A only because A charges less. But Y often sends data to X, so we should advertise to C too. Okay. So I'm guessing that what Team 7 meant by fair is that A will feel that it's unfair because X and Y, none of them are my customer, right? But B then should be sending it to C only, right? If X, Y are the only customers, are the only parties involved in the transmission. Okay, so what do you mean fair here? Okay, so if Polly is wearing a critical hat here, so it's a little bit vague what you meant by being fair. All right, but I think fairness is often a very good point to argue. And let's see, Team 6 says B to both because B gets same amount of money from A and C. Okay, so maybe I was not clear. I actually meant that B pays A, B pays C because A and C charge B. That means money flows from B, out of B's pocket to A and C's pocket. Yeah. So for Q1, I guess you guys will say, hey, it doesn't matter. For Q2, only to A. So C will send message to B through A. Okay, yeah, so B then pay less. So for Q2, if you choose to send advertisements only to A from B's perspective, that is going to be cheaper. Okay. Yeah, so I see in Team 4's solution only to A. Thinking again about money. And if you are B, not thinking like A, not thinking from A's perspective. Very good. Maybe to A, then we have some money, although then A may pay more money to C. Yeah, poor A. But you see that from a B's perspective, it seems that it's a wiser thing to do. After all, ISP is a business. In business, money is a very, very, very important metric. Yeah, I guess Team 7 is more a socialistic view. Yeah, and Team 4, Team 15, Team 6, you guys can consider, taking business courses. Okay, Team A definitely taking business courses. You do have the intuition of running businesses. Okay, yeah. If $sign is what matters. For Q1, doesn't matter. For Q2, definitely B advertised to A because A charges less. Now, let's move on to the next quiz. Okay, number 49. Okay, and scenario remain the same. All right, and let's assume B has already advertised BX to A and C. Okay, so B has already advertised BX to both A and C. And further, A advertises ABX to C. So in a way, provider C here learns two AS paths to X. One is CBX. The other is CABX. Now, look at the money flow here. C, being the oldest ISP, charges A more. And C charges B less to forward traffic. So what I'm trying to say here is that B pays C to forward traffic. A also pays C to forward traffic. Okay, hey, this is the reality. Okay, this is the fact. Suppose now you're hired by C. Now you need to think from C's perspective. Would you advertise CABX or CBX or both to Y? And provide your reason. Okay. Again, we don't have all that much time. So let's see. Oh, okay, we do have Team 7 here answering the question. Let's see. Whoopsie, sorry. So Team 7 is saying CABX. Because that way C gets more money. Exactly. Very good. Again, $sign is the key factor. And last quiz. This one is a little bit tricky. Okay, and we don't have time for you to think and then answer the question today. So quiz 50 is going to be a take-home quiz. Okay, so this semester we do have a couple take-home quizzes. So the scenario is a little bit more complicated. You see that in quiz 50. So I'm actually continuing from the two quizzes above. You see the money flow being like this. B pays A and C. A charges B, but A pays C. Okay, and the amount of money C is charging AB, A is charging B, are represented by the thickness of the airs. Okay. And now consider, okay, the money. CABX will be the path to forward traffic from Y to X. Yeah, because that way C profit the most, right? But hey, poor A. Okay. So the challenge now in quiz 50 is that pretend that you are hired by A. Q1 asks, would you raise or lower the price A charges B? Q2, would you negotiate with C to raise or lower the payment to C? If you are more engineering aptitude instead of business, can you come up with some other solution instead of talking just about money to change the situation? Well, in case B wouldn't raise, C wouldn't lower the charge. Q3, can you do anything to try to make it a little bit fair from A's perspective? So you cannot say B, you cannot advertise BX to me. Okay, B will advertise to you, but A, can you do something based on BGP routing policy setting so that it will be a little bit fair, okay, to A. All right, so this is the take-home quiz. We do have a summary video, which is just 1.5 minutes. Let's play that, and then we'll call it a semester, okay? The summary video of BGP.
Now the summary slide. So internet routing is hierarchical. At the lower level, intra-AS routing. At the higher level, inter-AS routing. Now there are three very good reasons for such separation. Okay? Because at the higher level, okay, the network admin would really like to be able to block transit traffic. So doing policy-based routing allows admins to do things flexibly. Okay? Now, in the intra-AS, however, then we can go entirely with the performance. Let's calculate strictly the shortest paths so that the delay to go from one router to another router will be the lowest. Third reason, separating internet routing to two levels is also to reduce the amount of memory requirement and to reduce the network bandwidth consumption. You see, Intra is running link state there. The amount of global information much lower, right? Because you're only keeping the information of the local area network. Amount of link state reports you need to send also lower because the number of routers in the AS lower. Similarly, in the backbone, okay, these border routers, okay, the amount of it lower. Therefore, amount of updates we need to send lower. Okay, and there's prefix for the destination. Okay, the higher we can aggregate the prefix, the memory requirement for the pass factor also lower. So, separations of internet routing into two levels.
All right, so that's all for the semester. Quiz 50, I guess, for example, 怀智, you are probably more engineering aptitude or more socialistic. Q3 here, definitely think about what would be the best way to do it, right? If you don't like money negotiation. All right, and you know what? What remains is just this Saturday, make sure that you finish the last 4 quizzes, and next Wednesday, come to the exam. Then we're all done. So Polly here is saying happy summer and best of the luck with the exams. And that's all for the semester. Bye. Oh, no? Okay, sorry. Okay. So I probably missed what you were saying there, Youyu. So if there was a question, just let me know. All right, so yeah, as usual, if you have any questions, just type them up, okay, either on Slack or the YouTube channels. Let's see. Okay, bye. I guess you guys are all busy trying to complete the quizzes earlier, right? Yeah, so there are 4 of them. Yeah, it's quite a handful today. No worries, take your time. Yeah, there's a lunch break coming ahead anyway. Okay, so you meant that you don't like politics? Yeah, human beings are complicated, definitely. Oh, thank you all for your patience throughout the semester. Jiahong, sincerely, okay, appreciation from Polly as well. You are very often the earliest student, okay, joining the YouTube session. Thank you, Wei Xiang. Thank you, Keke. And thank you, Tim. Thank you, Guan Yu. Thank you, Zhao Qi. Sure, thank you, Xue Han. Thank you, Amelia. Yeah. So we'll still see each other. However, you guys will probably be more nervous. Yeah, thank you, Hui Xin. And bye. Bye, Liang Xin. Bye, Doris. Yeah, thank you for the nice message, the kind, very warm. Yeah, thank you. And thank you, Jason. I see you guys are very active typing up solution for quiz 50. All right, so Polly is going to leave the session on for just a little bit longer. And bye, Yusho. Yeah, you picked up programming using Golang very well. That's great. That's a very practical skill. And bye, Yujie. Ah, time flies, isn't it, Yujie? Time always flies. I don't know if you noticed. Well, as you grow, as you go out to the society, you find a job and you start earning, you will accumulate wealth. You will earn more and more. But time, every day go by, each day, one day less in your lifetime. Okay, I think time is a lot more precious than money. All right. And bye, Catfish. Thank you for having these fantastic questions. Oh, you like the oh, okay. I like you guys as well. Yeah, I do notice something very interesting because I can sometimes be walking around the EE buildings and suddenly students greeting me and calling my name and I don't recognize you at all. So if that happens to you, hey, just tell me who you are. Yeah, so tell me you are Yujie, you are Youyu, you're Catfish, or Yusho, and then I will know. I'll know Yusho by heart that you are a very good Golang programmer now. Very fast. Yeah. Well, you see that I think most of you are, I think junior year. Yeah, after senior year, it's pretty much the society. And grad school is a kind of to simulate the society, the kind of studying you are doing there. For example, writing a thesis, that's independent work. And yeah, thank you, Cai Tong. Yeah, I wish I can see a video of you dancing. All right. Okay. Yeah, hi, Catfish. I think you have more questions you want to ask. So let me, hey guys, let me turn off the YouTube session and let me stop the stream now. Okay, bye.